Hello, my name is Davis Binger, and let's talk about the solutions to quiz number 2. The in-class portion of quiz number 2 asked us to use the general slicing method to find the volume of a given solid. The solid of interest has a base region bounded by the ellipse x squared over 17 plus y squared over 8 equals 1, and the cross sections of our shapes, which are perpendicular to the base and parallel to the x-axis, are semicircles. We will assume that the diameter of the semicircle lies along this base. The take-home problem considered a region R bounded by the graphs y equals negative x squared plus 2x and the x-axis. The first part asks us to find the volume of the shape formed by revolving this region about the line x equals 4. The second part of this problem asks us to find the volume when we revolve this solid around the line y equals a for a variable constant a. The third part asked us to find the value a, which made the volume in the second part equal to that of the first part. Let's proceed with solving each part. So for the in-class problem, we need to use the general slicing method. That means we need to find a formula for cross-sectional area as a function of position, that is, where we are, which slice we're taking. So the cross-sections parallel to the x-axis are perpendicular to the base. So if here's the x-axis, here's the y-axis, the cross-sections are coming in like this. And so they vary as y varies. So we will integrate with respect to y to find the volume. And we will need to find the cross-sectional area as a function of y. So we know that the cross-sections are semicircles. The formula for the area of a semicircle is 1/2 pi r squared, where r is the radius of the semicircle. To find the formula for cross-sectional area at a given height y, we need to find the radius of the cross-section corresponding to that particular height. So we will do this by solving the curves of the boundary of our base, which was the ellipse, for x as functions of y. So after doing this, you have two branches. You have the positive branch and the negative branch. So we know that the diameter of the semicircle sits along the base. So it travels from the left branch of this ellipse to the right branch. So that's the diameter. The diameter is twice the radius. So the radius is 1/2 of the difference of these two. In other words, it's just the square root of 17 minus 17 over 8 y squared. So cross-sectional area was 1/2 pi r squared. We found the radius. We can plug the radius in, and after squaring out the square root, our cross-sectional area as a function of y is pi over 2 times 17 minus 17 over 8 y squared. So we need to figure out what the bounds of integration are. We have cross-sectional area. Remember that the generalized slicing method said that we could find volume by integrating over the bounds of the region, the cross-sectional area. So we want to figure out what are the max and min y values of the base. So we do this by plugging in x equals 0 to the curve, and we find that the max y value is the square root of 8 and the min y value is negative square root of 8. So our volume So the integral from negative square root of 8 to the square root of 8 of pi over 2 times 17 minus 17 over 8 y squared dy. Note there's a small notational error here. Please don't forget your dy when you write this down. After taking an antiderivative, we get that the volume is pi over 2 times 17x times 17 over 24 y cubed, evaluated from negative square root of 8 to the square root of 8, which is this lovely expression right here. And we'll leave this in its unsimplified form. Alright, that wraps up the in-class problem. Now let's go through each part of the take-home problem. We find the volume of the solid of revolution formed by revolving the region bounded by the graph y equals negative x squared plus 2x and the graph y equals 0 around the line x equals 4. So we're given functions, they're functions of x. And we're revolving this region about the line x equals 4. Now think about x equals 4. X equals 4 is parallel to the y-axis. So it's like we're revolving around the y-axis. So if we want to integrate with respect to x and we're revolving around something like the y-axis, we need to use the shell method. So what do we need for the shell method? We need the height of our region as a function of x, and we need the radius, i.e. the distance from a point x to the axis of rotation, as a function of x. So our function isn't so difficult. We can easily calculate the values of intersection by equating the two and find that they intersect for values of x equal to 0 or 2. So we want to identify which is the top function. We'll just evaluate at the test point x equals 1. At x equals 1, negative 1 squared plus 2 times 1 is 1. So negative x squared plus 2x is the top function, and the height of our region is given by the difference of the two functions. Well, the difference of the two functions is just negative x squared plus 2x. Alright, so now we have the height and we need to figure out the radius. So we have a point x, and this is in the interval from 0 to 2. And we want to find what is the distance to the point 4. So this distance is going to be exactly 4 minus x. Thus we have our height, we have our radius, and we can find the volume by integrating 0 to 2, 4 minus x times negative x squared plus 2x dx times 2 pi. Now, we multiply through under the integrand, and now we can integrate using the power rule. 8x integrates to 4x squared, 6x squared integrates to 2x cubed, and x cubed integrates to 1/4 x to the 4th. We will evaluate this from 0 to 2, and after simplifying, this becomes 8 pi. It's good to get a simple form in this part. Looking ahead, remember we have to find the value of a for which the volume in the second part equals the first part, so we need a simple answer. Alright, part B. We're finding the volume of the solid of revolution formed by revolving the region about the line y equals a, where a greater than 1 is a constant. So we still want to integrate with respect to x. Our functions are still of x. But the line y equals a is more like the x-axis. So we want to use the washer-disk method. On the interval in question, our function takes on values between 0 and 1. This is important because the line we're rotating about is always above this graph. So the curve is closer to the axis of rotation than the x-axis. So this will be forming the inner radius, while the x-axis forms the outer radius. So the inner function will be the distance from the line to the curve, which is exactly a minus negative x squared plus 2x. And the outer radius is the distance from the axis of rotation to the x-axis, which is just a. So our volume is given by pi times the integral from 0 to 2 a squared times a minus negative x squared plus 2x squared. And we're integrating with respect to x. So there's some algebra here. You need to carefully square the second term. After you carefully square the second term, you have a squared plus x to the fourth plus 4x squared plus 2ax squared plus 4ax, or minus 4ax minus 4x cubed dx. Now, we simplify things a little bit and take antiderivatives using the power rule, come up with the following expression, for which we can evaluate from 0 to 2. After evaluating from 0 to 2, we come up with the following expression, which simplifies to pi times 8 over 3a minus 16 over 15. This ends part B, and we're ready to move on to part C. In part C, we want to find a line y equals a so that the volume we found in part B is the same as the volume in part A. So we need to equate the two results and solve for A. After dividing through by pi, we get 8 thirds a minus 16 over 15 is equal to 8. And 8 thirds a is equal to 136 over 15. A is equal to 17 over 5, which is 3.4. Alright, so that concludes my video of the solutions for quiz 2. Thank you for watching, and as always, you can reach me at binger@math.ohio-state.edu or by leaving a comment below. Have a good evening.